Okay, in our previous segment, we learned that you can start with one radioactive element, and then it can decay and turn into another radioactive element, and then that can decay and turn into another radioactive element. But we didn't mention anything about how much time it would take to do that in. And so that is what we want to discuss right now. So in radioactivity, let's pretend that you start with 100% of a particular radioactive substance. Okay, in a certain amount of time, it will decay to 50% of what it was. So 50% of the original radioactive element turns into some other kind of element. Now, the amount of time it's going to take that to occur in is going to be called the half-life. So that we're going to symbolize that with T for time, and then let's put a 1/2 on there. So this is going to be our symbol for the half-life. So this is going to be the amount of time that is going to go by in which you're going to start with 100% of some radioactive substance, and then in this amount of time, half of it will turn into some other radioactive substance. So we could graph this. So what we could do is we could have the percentage going up and down, and then we could have the amount of time it takes to happen going sideways. So in this graph, we start with 100% up here at time t equals 0. So the instant that you click your stopwatch, you start with 100% of some radioactive substance. Okay, at the end of one half-life, you're down to 50%. So this is 50%, so we'll go over to here and we'll put another dot. And then at the end of two half-lives, we're down to 0, right? Because if you lost 50% the first time, then you lose 50% the second time. So 50 plus 50 is 100. No, that's not right. So at the end of two half-lives, it's 50% of 50%. So what would that be? That would be 25%. So down here somewhere, this is going to be 25%. 50% of 50% is 25. So at the end of two half-lives, we're going to be right there. And so you do the third one. So if it was 3, what would we be down to? After 3 half-lives have gone by, you'd be at 50% of 25%, which is 12.5%, and you would be down to about here. And so if we were to take these things and put a curve through it, that's called an exponential curve. So we say this is exponential decay. Now, how many half-lives do you think it would take to get down to 0? An infinite number of half-lives, because this thing never gets to 0. You see it's curving like this. So it's like in geometry, an asymptote. So in an asymptote, you can never reach it. So similarly, this horizontal line here means that it takes an infinite amount of time for a radioactive substance to go to absolute 0 on there. Well, we can, this chart, this thing right here, can be represented mathematically. And so that's what that formula is. So that mathematical formula says N, which is going to be the amount of radioactive substance that is left over, is going to equal the amount of radioactive substance you began with, so that's N sub 0, and then the exponential of the negative of 0.693 times the amount of time that has elapsed, divided by what the half-life was. Now, every radioactive substance has its own half-life. So it depends on what the radioactive substance is as to what its half-life is. So here is an example of how we might use both the formula and a graph. So the easiest way to do one of these problems is to have a chart. So it says that a radioactive sample has a half-life of 100 years. So after 100 years have elapsed, half of the radioactive substance will have gone away. If you started off with 1,000 grams of this radioactive substance, how much would be left after 550 years have gone by? Okay, so we know the half-life is 100 years. We know that we're starting with 1,000 grams, and we need to know how much will be left over after 550 years. So we make a table. So in the first column of the table is going to be how much time has elapsed. So let's go ahead and build the table over here. So in the first column, we're going to have how much time has elapsed. So T for time. Now the instant we click our stopwatch, how much has decayed? None of it. So over here, we're going to put 1,000 grams. So this is the amount of radioactive substance that you have. So we could put M for mass. So this is 1,000 grams is the amount you start with. Now after one half-life, so how many years? 100 years is one half-life. We're going to have half of this, so it's going to be 500. And then after two half-lives, so now we're up to 200 years, we're going to have half of this, it's going to be 250. Okay, and you just keep going down, filling in this table until you get to around 550. Now the problem is you can go to 500 and you can go to 600, but you can't go to 550. So all that we can say is that our final answer is got to be between 31.25 and 15.63 grams are going to be left over. That's as close as we can get. But we could also do it using mathematics. Now, you're not going to have to do this on the exam. So you're going to have to be able to make a chart like this on the exam. But you're not going to have to do this, but I just wanted to show you. It's not too difficult. On your calculator, you should have a button that says e to the x. So the e to the x button is your exponential button. And so you can use that in order to solve it. And the exact answer is 22.1. Okay, now let's go back. And is 22.1 in between 31.25 and 15.63? It is. So that's a pretty good indicator that we did the right job when we used the formula for it. Okay, so here, this chart shows you the half-lives of different radioactive substances. So do you remember from, let's go back to this chart here. Okay, if you remember that chart, we started off with radioactive uranium, and then it turned into, what was it, thorium? So if we go back to here, starting off with uranium and then turning into thorium, you see how long is it going to take for half of the uranium to decay? And you can see it's a very, very long time. Okay, so it's in terms of billions of years. But then notice that some of those numbers are very small. So some radioactive substances decay very quickly. So that means that as far as danger is concerned, you don't need to worry about those radioactive substances because they decay so quickly. But then there's the other ones. So look at all of this radioactive waste that is going to be produced by a nuclear power plant. Okay, let's take a break. When we come back, we're going to now talk about a nuclear power plant and how it works.